Hello, my name is Aditya Pillai, and this is Lab 3, Black Hole. This lab was conducted with several objectives in mind, including modeling the orbit of a star around a black hole, analyzing the motion of the star in order to estimate the mass of the black hole, and applying key physics concepts such as Newton's second law, gravitational force, and force components parallel and perpendicular to the motion of an object. The purpose of this lab is to model the gravitational motion of a star about a black hole in order to analyze the perpendicular and parallel forces, as well as to calculate the estimated mass of the black hole. Some of the key physics concepts applied in this lab include the following. Newton's second law of motion, which can be derived from the momentum principle. From here we can derive the second concept applied, the concept of parallel and perpendicular components of the change in momentum. And finally, the gravitational force equation is the third concept applied. As part of this lab, since we can't realistically go and measure the path of a star orbiting a black hole, we were given this information. The black hole is at the origin. The mass of the star is 2 by 10 to the 30th kilograms. The position of the star is calculated for us using our GT email. The net force is due to the black hole and only the black hole. And the time between data points is 1 day, or 24 by 60 by 60 seconds. Once given the server code, we were instructed to alter the code to function properly. The first change is to replace the seed with our GT email and generate a unique star path. Then we were to edit the star.m variable and the delta t variable to fit the given values of 2 times 10 to the 30th and 24 times 60 times 60. Then we had to calculate the initial and final momentum using the velocity vectors. This can be done using the definition of momentum, which is mass by velocity. To calculate the delta v and delta p values, all we had to do was subtract the initial values from the final values for velocity for delta v and momentum for delta p. To calculate the change in momentum over time, we simply divide the change in momentum delta p over the change in time delta t. Since this is proportional to net force, you can set the net force variable Fnet equal to this change in momentum over change in time. The direction of the initial momentum p hat can be calculated using p initial divided by its own magnitude to get the unit vector. The change in momentum over time can be calculated by the differences in the magnitude over the time frame divided by the length of the time delta t. We can then calculate dp dt parallel using the initial direction and change in momentum that we had just defined. Since this is equal to the parallel net force, we set Fnet parallel equal to this. Since dp dt parallel and the perpendicular component added together equals the net change in momentum over time, subtracting the parallel component from dp dt gives us dp dt perpendicular. Using this, we can also define Fnet perpendicular. And finally, to calculate the mass of the black hole, we find the distance between the star and the origin represented by the variable r, and then alter the equation for universal gravitational force shown earlier to find just the mass of one of the components, in this case, the mass of the black hole. So this is what the code looks like when it is run. As you can see, the orange arrow represents the net force, which always points at the source of the force, in this case the black hole. The pink arrow represents the perpendicular force, which always points toward the center of the kissing circle and represents the change in the object's trajectory. And the blue arrow represents the parallel component of the force, which points either parallel or anti-parallel to the motion of the star, and indicates whether the object is speeding up, slowing down, and by what magnitude. The code prints out the mass of the black hole at different time intervals, and then the magnitude of the net force and net force components at the end. After the lab, we were to answer 2 post-lab questions. The first asks, in your analysis, you should discuss how the net force and its parallel and perpendicular components are different from the rate of change of momentum and its parallel and perpendicular components. The answer is that while the numeric values of both are the same, they represent very different things. The change in momentum and its components represents the physical phenomena we can observe, the outcome of the influence of the net force and its corresponding components. The momentum change is the outcome of the net force, and therefore not the same thing. The second question is, imagine the black hole whose mass you found was removed and a different one replaced at the same location. Assume that the motion of the star remains unchanged and is affected only by the gravitational force of the black hole. Could you tell the difference? The answer is no, because observations in this lab were based off of the physical changes we could observe. If those changes did not occur any differently than they did before, there's no way of telling that the object is any different than what it was before. In conclusion, it is helpful to use Newton's second law of motion, universal gravitational law, and force component equations in order to visualize scenarios and identify unknown values. From these concepts, the average black hole mass was calculated to be 1.45 times 10 to the 34th kilograms. The average net force magnitude was calculated to be 9.216 times 10 to the 28th newtons, with average parallel component 1.39 times 10 to the 28th newtons and perpendicular component magnitude of 9.117 times 10 to the 28 newtons. Since we didn't record the data ourselves, instead it was visualized by a model, we don't know if there were any deviancies in the observation of the star. The computational model shows the black hole as having a changing mass, which can't be confirmed, though seems unlikely. Thank you for listening.